Good afternoon, and this is Chi Lee. I'm a postdoc at IBM and under co-supervision of at UIUC under Eric Baum and Sanjay. I apologize for this remote presentation, and also I thank you for people who haven't left yet for your interest in some physical science-oriented talk. Okay, so my talk today is on the ground state calculation of OpenAtom. So what we're really interested in here is we are trying to calculate the electronic structure of a large-scale and complex systems on a large-scale parallel architecture. For example, we have here the next generation post-CMOS transistors, and we are interested in looking at the membranes, the DNA sequence, and the solar cells. These are all complex systems. By complex, I mean your simulation box is really large. You have hundreds and thousands of atoms, and which is typically very large problems for first principles calculations. So, again, here we're collaborating very actively with UIUC team, and typically we write the serial code and then hand them over to UIUC, and they will charm plus it for us. And also we have another group of collaborators at Yale. They are concentrated on the excited state calculations, as we'll hear later in this talk. So here is a little background of Kohn-Sham DFT. So if you want to calculate the electronic structure of a system of many atoms and all the electrons spinning around it, it's an overwhelmingly complex system. And to solve that, Dr. Kohn, he proved the existence of this way to turn this many-body problem into a one-body problem. And the only unknown here is the local density, which can be decomposited into a series of Kohn-Sham states orthogonal to each other. And the number of Kohn-Sham states here is the number of electrons divided by 2. So one state can accommodate 2 electrons spin up and spin down. So once you establish the local density, this DFT theory, your total energy is actually functional of the local density. So it can be decomposed into 4 terms: the kinetic energy, Hartree, which is the electron-electron, and the external energy, which is the electron-ion. And the first 3 terms are easy. And the last term is the exchange correlation, which is a bit more complex, and people have developed different kinds of methods. And here we just adopt one of the popular ones. It's called GGA, the Generalized Gradient Approximation. Basically, what it does is it takes into the both the density and the gradient of it to calculate this energy term. So currently, Kohn-Sham DFT is already implemented in OpenAtom. As you can see this figure, and you'll see more and more figures throughout our talk. And basically, they just, from different aspects, it says one thing: OpenAtom is faster than anybody else. So then the reason behind this is we have better maths, and we are doing everything under the charm++ framework. There's one problem though. Currently we're using the so-called norm-conserving pseudo-potential, which requires a large basis set, and so it's memory demanding and it makes your calculation slower. And so to solve that problem, we introduced this so-called PAW method, Projector Augmented Wave. What it does is it splits up the total Kohn-Sham states into a smooth part, the delocalized part, and the localized part closer to each atom. So, which enables us to use a smaller basis set even for heavy atoms, like transition metals, and also some other method also uses this idea, but PAW is quite good because it has a very good transferability. It's easy to generate, and it has accurate information about the core states, which sometimes people are really interested in it. So, however, PAW is implemented in other first principles software as well, like VASP, and everyone has it. But the problem is their scaling is n cubed, and their parallel performance is quite poor. So our goal here is we want to have better scaling by using EES, which I'm going to explain later, and we also want a better parallel performance. So here's a bit of math. Forgive me. So the total Kohn-Sham state psi I can be split up into a smooth part and a core part. The core part has the contribution of every atom in your cell. So number of atom is n, and big J is the atom index. And this core function psi ij, it lives only inside some cutoff radius RPC, which we call the augmentation radius. And the smooth part is easy. We do the standard plane wave expansion. The core part, we can construct it by using these two projector functions, delta p and ps, and both of them live only inside the core. So if you zoom out and you look at the whole simulation box, it's kind of like this. Around each atom center, you have this core wave function. It's wiggly, and it's harder for if you want to do it in G space. But between these cores, you have the smooth part wave function, which is easier to deal with in the G space. So we like to call this the fruit and in the jello model. And so the complex thing is the cores interact with each other, the cores interact with the smooth part. And so, for example, if we substitute in the expression for the total energy functional, for example, the kinetic energy term now expands to 3 terms: the smooth interaction, smooth core, and core. And another example is the electron density, and because many of these terms, it depends on electron density in the real space. And so similarly, it's decomposed into 3 terms, which adds more complexity. But the good thing is this complexity added in there doesn't scale, which I will explain later. So for the Hartree energy and the electron ion external energy, because you have no truncation scale for the 1/r term, we use an additional trick, the E-volt decomposition, to split up the 1/r term into a ERF-C plus ERF function. So the ERF function, which have a long tail, we just solve it in the G space by using Poisson summation. So the short term, which is truncated by this ERF-C function, we just solve everything in the real space. That's the plan of attack. So here it shows how accurate we can do this E-volt decomposition. It's just a really simple method to show. So if we choose the cutoff radius of the eVolt to be 4 Bohrs, which is the typical value of the distance between two atoms in our system. So by doing this, you don't have to include nearest neighbors. And here, as we can see, if we go to 30 Rydbergs, we already have quite good accuracy, which means our plan is doable. Also, if we choose RC to be bigger, like you can do it for 8 Bohrs, even 10 Bohrs, and in that case, we can further reduce the plane wave cutoff, meaning you can use even smaller basis set, and that's the whole point of doing PIW, of course. And in that case, you might want to, you have inside each cutoff radius, you have multiple atoms, but we just have one new complexity, it's the nearest neighbors. So we just add all the nearest neighbors up, which also doesn't scale with the system size. Okay. So here are the two main theorems based on which we establish our whole implementation. The first one is a sampling theory. Basically, what this says is if you have an FFT from FR to FG and you want the G-space coefficients for FR to its m's power, you just need to sample FR m times more densely than FR, and then you can do this with an FFT exactly. And FFT can be done in n log n. And the other theorem is the EES. It's a most important theory in our whole method. So if you think about all these terms, for example, this SG term, we call it structural factor. We use it pretty much everywhere in our throughout our calculation. So this exponential of Ig dot r, this r, if it is for each atom, so you have so this little r, actually I should write r as a function of j, the big R as a function of j. So actually, if you want to solve this term term by term and add all of them up to get Sg, you have to do it for every atom, which scales as n, and you have to do it for every g, which also scales as n, so you end up with n squared scaling. And if we can do FFT and get all these SGs all at once, we can do it in n log n. It's a good thing. However, you can't do it directly because remember your atoms, they don't have to land on a regular FFT grid necessarily. So our plan is to use the EES method. If you look at the equation down here in this second box, so for any atom, no matter it lives where it lives, so this S, you can find this EES, and so dP is just a weighting factor, so to enable your EES. And the good thing about this method is, as you can see, this MP term, it has compact support. It only has P values, where P is a spline order. We choose 6 or 8 or 10. P finite non-zero points, non-zero values. So on each direction, x, y, z, and the error term is here, and we can control the error term by using an even denser FFT grid. So here I show you some basic operations of doing the EES. So the big box is our FFT box, and all these dots are the FFT points, and the sphere is the G-space cutoff. So we can do an FFT from G to the real space. Also, we can also use the density grid, which is twice as denser in the real space, and we FFT back, so we get the plane wave coefficient for the electron density in the G space. As you can see, the sphere grows larger. That's because the G space cutoff for the density is larger. Okay, so and you can also do ES on the density. So here, for example, you have a function in the real space, and it interacts with every atom, and you want to find, and however, only a portion of the FFT grid interacts with some specific atoms. So for atom 1, only the FFT points in the little box interacts with is associated with atom 1, and so finding this little box can lead us to some quantity in the real space around each atom. And similarly for the density. And sometimes we are not only interested in the center of the atom, we are interested in some quantity like the density in the vicinity of the atom, and because we want to do a numerical integral, and we define an F grid, a very fine spherical coordinate grid in the real space, and in this case, each F grid point is associated with one FFT grid. So actually, you end up with a larger little box here, but it's okay because even these boxes overlap. What we are really interested in is the points around each atom, so we can get the quantity we want. And the important thing here is the NF, the number of points, real space points in the F grid, or the B-spline points. These points, typically it's P by P by P, where P is your spline order. Neither of them scale, so which is the good thing. Scalability is all what we care. And to wrap up, I'll just explain some of these new terms. And actually, we have constructed more terms, but just for example, I'm going to show you how we get the local density, which are needed in the PAW implementation. So the first one is the smooth density inside the core. So to calculate that, first we multiply. So first we have to calculate the electron density in the G space, but that's easy. And we multiply it by dg, which enables your FFT, the weighting function. And then you do a big giant FFT, and so you get the E as weighted smooth density in the real space. And then you do the M partition, and you find the FFT points associated with each atom J, and from there you can do a B-spline and get the density on the F grid around each atom. And similarly, for the core 1 part of the density for each atom, similarly you multiply your psi I with the ES weighting factor, and then you get the ES weighted Kohn-Sham state in the real space. And then for each one atom, you add up all these Kohn-Sham states, you multiply them by the Z matrices, and then for each atom you just add up all the Kohn-Sham states, nks. You have nks atom, and then you can find the associated FFT points around for each atom. And finally, guess what? You do B-spline again, and you get all the density around each atom. So here it's an example of what we are going to do after we implement PIW. So this is a very, I can say, a very hot material in the solar cell field. It's called Perovskite solar cells, and the efficiency of this material is reaching the silicon, so it's really great. But the bad thing about this material is very unstable. It pretty much dissolves in anything. So we're trying to look at what's happening there, and for example, we can expose this material in water and run some MD, and we can also look at some other directions. And the two main point here is, so first we have a very heavy metal elements here, so PIW really plays an important role. Also, we have quite large system, so that's why pretty much nobody else can do it, like at this point. So OpenAtom does a very good job in these large scale systems. So that was it. Thank you for your time, and if you have any questions, I'm here.
All right, let's thank the speaker. Thanks, G, for joining remotely.
Thank you.